As we continue our study of kinematics, we're going to look at the next section, which involves vectors and scalars. Vectors and scalars is a pretty big topic in physics, or one that carries through a number of different chapters. So we're going to take some time to differentiate between those two and then see how they apply to the study of motion where we're at right now. So in general, a scalar is any number that does not have a direction with it. So just a size. So if I said 30 miles, but I didn't say in what direction, that's a scalar. To make it a vector, it has both a size and a direction. So if I said 30 miles east, then that would be a vector. In physics, you can describe direction in a number of different ways. You can use degrees or even compass directions, anything like that, but there has to be a direction associated with it for it to be a vector. In the section that we're at right now, we're talking about distance, speed, and velocity, things like that. Those can be divided up into scalars and vectors. So in physics, the physics meaning for distance is the length of the path that you took. So if you walk 5 meters one way and then you return to where you started by walking 5 meters back, the total distance that you've traveled is 10. But displacement describes how far you are from where you started. So in that same situation, your displacement would actually be 0 because you end up where you start. Or if you had walked 5 meters one way and 4 meters back, then your distance would be 9, but your displacement would be 1. So that's the difference between those two. How that relates then to the next thing is speed. So how fast something's moving without a direction is considered speed. If you include what direction you've gone, then it's velocity, which is a vector. Notice that speed usually has a symbol v, just like velocity. So a lot of times, just by looking at the numbers in a problem, it's hard to tell if something is indicating speed or velocity, or if you just are given an equation. You need to look at the context and what else is given in the question. So as far as their equation, speed then is distance over time, where velocity is displacement over time. So those are just by definition, and we'll go through some examples to see how that really plays out when you're problem solving. So here's the first example. So a car drives 5 miles east and then 3 miles west. So this is similar to the example I gave before. So what's the total distance traveled? It's going to be 8 miles. But what is the displacement? The displacement is actually going to be 2 miles, and I probably should have included it's going to be 2 miles east, meaning east of where it started from. So here's example number 2. So we've got an airplane flies 200 miles in 1 hour, and then it returns to where it started in 45 minutes. So how far did it go? And you can see from my diagram, it's pretty clear it went 400 miles. So the distance traveled is going to be 400. But how far is it from where it started? It's going to actually be 0 miles from where it started, so its displacement then is 0. So I consider this sometimes a trick question in physics when they ask you for displacement. Like, you just really want to say 400, but you just have to remember the term that they're using and the definition that goes with it. So displacement here is 0, even though the plane did actually move. If I want to look at the speed, then speed is going to be distance over time. We already said the distance was 400 miles, and the time given here is 1 hour and 45 minutes, so 1.75 hours. So there's my speed. What's my velocity going to be then? Velocity is going to be displacement over time. So since the displacement is 0, the average velocity is actually 0 as well. And that's another one that it feels uncomfortable to say that, but then again, that's the physics definition for how you find velocity. Okay, another place that you'll see this is in reading graphs. So this is a velocity time graph, and we've said that the area underneath a velocity time graph is actually distance if you don't include the direction, or displacement here if you do. So the distance traveled here is 10 meters per second for 5 seconds, so that's going to be 50 meters. So in this case, the displacement is actually going to be the same. So the question is, why is the displacement the same in this case? The answer is because you've gone the same direction the entire time. When there's not a change in direction, you're going to find that distance and displacement are the same, as well as speed and velocity. So in this case, the speed is going to be the distance over time, which is 5 seconds, and the velocity will be the displacement over time, which is also going to give you 10 meters per second. So the same answer on those. Again, the reason for that is because there's no change in direction. Those quantities will all be different from each other if you've changed direction during the problem. So here's an example of that. So this is a position time graph, and you can see as you go from A to B, you're going forward, and then the segment B, you're actually not moving at all. So there's no change in position here. But when you take the C segment, you start at 300 meters and go down to 200 meters. So there's our change in direction, and that's going to affect how we answer the rest of the problem. So the distance traveled is the entire length of the path. One way to say that is that it's the sum of each line segment's distance, but the absolute value. So we're disregarding sign when we add those up. So in this case, if I sum all those together, I've got 200 plus 0 plus 100, again, I'm going to make that positive, plus 400 plus 200. So I sum all of those and I should get 1,000. So if I want to find the displacement, regardless of what happened from where I started to where I finished, all I have to look at is how far the final spot is from the initial place. So it ended at 800. And it started at 0. So the change in position is 800, regardless of how much you go backwards in the middle or how long it takes even. Okay, so the average speed, then I'll do that distance divided by time. So that's going to be 20, but then the average velocity will be different in this case because the displacement and distance are not the same. So if I do the 800 divided by 50, I'm going to get 16. So that's an example of a problem where you have a difference between distance and displacement and a difference between speed and velocity. And the reason for that is because there's a change in direction involved. Okay, in general, there are 4 different ways that are commonly used to represent motion. One is just by describing it with words. So you could write kind of a simple sentence or a couple sentences that explain it. An equation actually also describes motion. So like V equals, some equation that goes with that. Graphs are a nice visual representation, and we've already been working with those quite a bit. The 4th one is something called motion maps. The easiest way to explain motion map is when we did the buggy lab, and you guys dropped a penny every second or every 2 seconds. When you were done, you were left a path of pennies. The distance between those pennies and kind of the pattern that those pennies make can be used to describe motion. If those pennies are a certain distance apart, or if there's a changing distance as time goes on. So there's a separate video that's not one that I've made, but a different video that I'm going to assign that will explain motion maps a little bit better, and we'll do some work with those. Out of the 4 representations, motion map is used sometimes, then you need to be able to understand them, but it's probably the least powerful way to represent motion. Okay, so in this video, you should have seen what the difference between scalars and vectors are, the difference between distance and displacement, and the difference between speed and velocity. For each of those, you should be able to calculate them, and you should be able to find each of them using a graph. If you've mastered that bit, you are good with this section. Thanks for watching.